magnetic field. What produces a magnetic field? There's a magnetic field around a permanent magnet. There's a magnetic field around a conducting current. From where does the magnetic field come? The answer is, it comes from moving charge, current. A charge set up an electric field whether the charge is at rest or in moving. A charge set up a magnetic field only if it is moving.
This lodestone is a rock composed of naturally occurring magnetic ore. When we hold a bar magnet near the lodestone, it reacts just as if it were another bar magnet, showing attraction between unlike poles and repulsion between like poles. These two bar magnets will be used to show magnetic attraction and repulsion. One of the magnets is placed on a bearing stand and the other brought nearby, first with unlike poles together. The magnets are attracted to one another. Now with like poles together. This time the magnets repel one another.
The definition of magnetic field B. Similar E equals Fe over Q. Moving charges in the magnetic field are exerted by a force. If a magnetic monopole were available, we could define B in a similar way. Because such particles have not been found, we must define B in another way. We fire a test charge Q through the point where B is to be defined. Using various directions and the speed for the particle, the charge will be exerted a force Fb. Now look at this one. This is in the Earth's magnetic field. Okay, we have a charge. They twist because they will exert a magnetic force. This is a magnetic field, a strong magnetic field. We see when something happens, you have a two particle. One is negative charge, one is positive charge. It's different. Okay. Let's see the facts. The magnetic field can deflect the test charge sideways, but it cannot change the test charge kinetic energy, the speed. Second fact is, a magnetic field exerts no force on the charge in one direction, only in one direction. Other direction, it doesn't have a force. 3. The maximum value of the deflection force is at right angle to this direction, no force direction. 4. The magnitude of the deflecting force is directly proportional to Q and to V. 5. The direction of the magnetic deflection force depends on the sign of Q. Positive and negative test charges with equal velocity being deflected in opposite direction. We see these 5 facts. Do you remember that? Now, mathematician can help us remember this one. Okay. We can summarize all these results with the following vector equations. Fb equal QV cross V. Fb is the force acting on the charge. Okay. This is the charge Q. That's the velocity of the particle. This is the magnetic field. Okay. That is, the force Fb or the particle is equal to the charge Q times cross products of its velocity and the magnetic field B. The force Fb acting on a charged particle moving with velocity v through a magnetic field B is always perpendicular to V and B because this is a cross product. So F is always perpendicular to V and B. Now, let's see how powerful this formula. It can explain our 5 factors. Factor 1. The magnetic field can deflect the test charge sideways. Now you have F. Sideways, F is always perpendicular to B and B. But it cannot change the test charge's kinetic energy because it's perpendicular, so you never change accelerate or decelerate V. Factor 2. A magnetic field exerts no force on the charge in one direction. Now, if V is parallel to B, V cross B equals 0. In this direction, in B direction, so no F, only one direction. The maximum value of the deflection force is at right angle to this one. Now, when it's 0, you get 0. When it's perpendicular to maximum, because VB equal to VB sine theta. Theta is 90 degrees, perpendicular to this one, F is maximum. Factor 4. The magnitude of the deflecting force, F, is directly proportional to Q and to V. 5. The direction of the magnetic deflecting force depends on the sign of Q. Positive and negative test charges with equal velocity being deflected in opposite direction. You see how powerful it is equation? Okay. You have to remember this one. FB equal Q V cross B. Now, we use the right hand rule. If this is a positive charge, Q is positive. This is the direction of velocity V. This is angle phi between B and V. So we use the right hand, curl our fingers from V to B. This is V cross B, F direction. And this is V cross B. If it's a positive charge, and this is the same direction. Okay. If it's negative charge, and this is opposite direction, it's going down, this is FB. Okay? Remember, this is FB, this is V cross B. You have it designed by the sign of the charge. We can rewrite this, the magnitude, the FB equal to QVB sine phi. The phi is the angle between the V and B. The metric system unit for B is Tesla. 1 Tesla is about 10,000 Gauss. Okay. Now, let me review it. V cross B. First, we use our right hand and extend 4 fingers along the direction V. Then we rotate from V direction to B. Okay, so this is your thumb, extended thumb is the direction of V cross B. Okay, V cross B. Now, if this is positive charge, so this is V cross B, the FB, the same direction. If it's a negative charge, so the FB is opposite the V cross B direction. Okay, V cross B is always the same, never changes. FB designs the sign of the charge Q. Let's see some magnetic field. The smallest one is this is very small, 10 to the minus 14 Tesla. And the biggest one at the surface of neutron star is 10 to the 8 Tesla. And our Earth is about 10 to the minus 4 Tesla, 1 Gauss, 0.5 to 1 Gauss. Magnetic field line. We can represent magnetic field with magnetic field lines, just as we did for electric fields. Similar rule applies. That is, 1. The direction of the tangent to a magnetic field line at any point gives the direction of B at that point. And 2. The spacing of the lines represent the magnitude of B. The magnetic field is stronger when the lines are closer, and conversely.
Here is a single bar magnet. If we sprinkle iron filings on a glass sheet sitting on top of the magnet, the filings fall into a pattern which shows the shape of the magnetic field. Here are two magnets with like poles facing. Here are two magnets with unlike poles facing. Here are two parallel magnets with like poles facing. Here are two parallel magnets with unlike poles facing.
Figure A shows how the magnetic field near a bar magnet, a permanent magnet in the shape of a bar, can be represented by magnetic field lines. The lines all passing through the magnet, and they form closed loops. Even though they are not shown closed in the figure, all lines are closed. Okay. The end of a magnetic from which the field lines emerge is not originated. Emerge is called the north pole of the magnet. The other end, where the field line enter the magnet, is not ending. Okay, is called the south pole. So magnetic field line is different from the electric field line. Opposite magnetic poles attract each other, and like magnetic field poles repel each other. The external magnetic effects of a bar magnet are strongest near the end. This is stronger. See, the line is closer, okay? It's closer. Okay. In the northern hemisphere, the magnetic field lines always generally point down into Earth and towards Arctic. And in the southern hemisphere, they generally point up of the Earth and away from Antarctic, that is always from Earth's geometric south pole. So from this one, we know that the magnetic pole and the geometrical north pole is opposite. Okay, in the north pole of Earth, we have south pole magnetic, and in the south pole of Earth, we have a north pole of magnetic. Sample. A uniform magnetic field B, okay, with magnitude 1.2 million tests is directed vertically upwards throughout the volume of a laboratory chamber. This is we look from up down. It towards you. It goes up. Okay. A proton with kinetic energy 5.3 million electron volt entered the chamber, moving horizontally from south to north. Not moving from south to north. This direction V. What magnitude diffraction force acting on the proton as it entered the chamber? I want to find this one. Okay. The proton mass is 1.67 times 10 to the minus 27 kilogram. We neglect Earth's magnetic field. One is only 10 to the minus 4 Tesla. Okay. Much smaller than this one. Now, see. Formula, okay, you want to find the formula, okay, F equal to QV cross V. Here we have a Q, okay, we don't have V, but we have a kinetic energy, and we have B, so it looks like this is a very simple question, okay. The B, we know that, kinetic energy, we know that, Okay, the mass, we know that. We want to find a V. Okay, we know K is kinetic energy is half mv squared. Okay, this is mass of proton. So we find a V. Very simple. 2K over m. We get the number. Once we get the V, we can get the F. QVB sine phi. This phi is 90 degrees. Okay, so we have a Q, we have a V, we have a B. Sine phi equal to 1. That's very simple. Okay, this is a simple mathematics. We get answer 6.1 times 10 to the minus 15 Newton. It's very small, very small. Okay.